Thermoelectric generators are devices that convert heat directly into electrical energy, using a phenomenon called the Seebeck effect. History: in 1821, Thomas Johann Seebeck discovered that a thermal gradient formed between two dissimilar conductors produces a voltage. At the heart of the thermoelectric effect is the fact that a temperature gradient in a conducting material results in heat flow. This results in the diffusion of charge carriers. The flow of charge carriers between the hot and cold regions in turn creates a voltage difference. In 1834, Jean-Charles Athanase Peltier discovered the reverse effect, that running an electric current through the junction of two dissimilar conductors could, depending on the direction of the current, cause it to act as a heater or cooler. Efficiency: their typical efficiencies are around 5 or 8%. Older devices used bimetallic junctions and were bulky. More recent devices use highly doped semiconductors made from bismuth telluride, lead telluride, calcium manganese oxide, or combinations thereof, depending on temperature. These are solid-state devices and unlike dynamos have no moving parts, with the occasional exception of a fan or pump. For a discussion of the factors determining and limiting efficiency, and ongoing efforts to improve the efficiency, see the article Thermoelectric Materials, Device Efficiency. Radioisotope thermoelectric generators can provide electric power for spacecraft. Automotive thermoelectric generators are proposed to recover usable energy from automobile waste heat. Uses: thermoelectric generators can be applied in a variety of applications. Frequently, thermoelectric generators are used for low-power remote applications or where bulkier but more efficient heat engines such as Stirling engines would not be possible. Unlike heat engines, the solid-state electrical components typically used to perform thermal-to-electric energy conversion have no moving parts. The thermal-to-electric energy conversion can be performed using components that require no maintenance, have inherently high reliability, and can be used to construct generators with long service-free lifetimes. This makes thermoelectric generators well suited for equipment with low to modest power needs in remote uninhabited or inaccessible locations such as mountaintops, the vacuum of space, or the deep ocean. Common application is the use of thermoelectric generators on gas pipelines. For example, for cathodic protection, radio communication, and other telemetry. On gas pipelines for power consumption of up to 5 kW thermal generators are preferable to other power sources. The manufacturers of generators for gas pipelines are Global Thermoelectric and Telgen. Thermoelectric generators are primarily used as remote and off-grid power generators for unmanned sites. They are the most reliable power generator in such situations as they do not have moving parts, work day and night, perform under all weather conditions, and can work without battery backup. Although solar photovoltaic systems are also implemented in remote sites, solar PV may not be a suitable solution where solar radiation is low, that is areas at higher latitudes with snow or no sunshine, areas with lots of cloud or tree canopy cover, dusty deserts, forests, etc. Global Thermoelectric has hybrid solar TEG solutions where the thermoelectric generator backs up the solar PV, such that if the solar panel is down and the backup battery backup goes into deep discharge, then a sensor starts the TEG as a backup power source until the solar is up again. The TEG heat can be produced by a low-pressure flame fueled by propane or natural gas. Many space probes, including the Mars Curiosity rover, generate electricity using a radioisotope thermoelectric generator whose heat source is a radioactive element. Cars and other automobiles produce waste heat. Harvesting that heat energy, using a thermoelectric generator, can increase the fuel efficiency of the car. For more details, see the article, Automotive Thermoelectric Generators. In addition to automobiles, waste heat is also generated in many other places, such as in industrial processes and in heating. Again, the waste heat can be reused to generate electricity. In fact, several companies have begun projects in installing large quantities of these thermoelectric devices. Some companies include TEGPRO, Thermal Electronics Corporation, Custom Thermoelectric, 2, Marlow Industries, TechTech MFR, Wellentech and TEG Power. Other companies are developing consumer-level applications to capture the energy commonly wasted during cooking. A handful of USB cooking products have emerged, such as the BioLite stoves, Hatsuden Thermoelectric Cookpot Stove Lite, light up your room with your wood stove stealth power systems, and the Power Pot. Wood stove TEG12V DC24AI and TEG12V DC24 liquid TEG generators producing enough power to trickle charge 12 VDC and 24 VDC batteries. Thermoelectronics Corporation. Devilwatt wood stove thermoelectric generators produce as much as 50 watts of power. Devilwatt Regulator thermoelectric generator energy harvesting modules convert very low voltage into regulated outputs of 1.8, 2.2, 3.0, 3.3 and 5.0 volts. Microprocessors generate waste heat. Researchers have considered whether some of that energy could be recycled. Solar cells use only the high-frequency part of the radiation, while the low-frequency heat energy is wasted. Several patents about the use of thermoelectric devices in tandem with solar cells have been filed. The idea is to increase the efficiency of the combined solar thermoelectric system to convert the solar radiation into useful electricity. The Maritime Applied Physics Corporation in Baltimore, Maryland is developing a thermoelectric generator to produce electric power on the deep ocean offshore seabed using the temperature difference between cold seawater and hot fluids released by hydrothermal vents, hot seeps, or from drilled geothermal wells. A high-reliability source of seafloor electric power is needed for ocean observatories and sensors used in the geological, environmental, and ocean sciences, by seafloor mineral and energy resource developers, and by the military. Limitations: besides low efficiency and high cost, two general problems exist in such devices: high output resistance and adverse thermal characteristics. High output resistance: in order to get a significant output voltage, a very high Seebeck coefficient is needed. A common approach is to place many thermoelements in series, causing the effective output resistance of a generator to be very high. Thus power is only efficiently transferred to loads with high resistance. Power is otherwise lost across the output resistance. A generator with very high output impedance is effectively a temperature sensor, not a generator. This problem is solved in some commercial devices by putting more elements in parallel and fewer in series. Adverse thermal characteristics: because low thermal conductivity is required for a good thermoelectric generator, this can severely dampen the heat dissipation of such a device. They are only economical when a high temperature can be used and when only small amounts of power are needed. See also. References. External links: Small Thermoelectric Generators by G. Jeffrey Snyder, Canilos, M. Tapping America Euro Unregistered Trademark S. Secret Power Source. Retrieved from Greentech Media, October 30, 2009. Website, http://www.greentech.media. Read, Lieutenant Journal October 2010, Ultra-Low Voltage Energy Harvester uses Thermoelectric Generator for Battery-Free Wireless Sensors, BioLite Camp Stove, Biofuel Stove and the Mo Generator in one. Description of Thermoelectric Generators, Thermoelectric Generators Basics, How Thermoelectric Generators Work, What are Thermoelectric Generators, Firepower TEGs, Hatsuden Wood Stove Thermoelectric Generators, Thermoelectric Generator Energy Harvesters.